So you built all kinds of things there. But that wasn't built, wasn't built for mathematical anyway.
No,
Anyway, tell me, where do we see you in all of me now? Haven't been seen.
I've just been up to see you for a second.
I move on to the main business of this afternoon, but the interesting business of this afternoon. And I'm going to sit down and shut up, because the John Fair Club is going to chair the proceedings. Undoubtedly, you are aware that John Fair Club is a lot more prominent past president of BCS than I am. But in case you are not completely familiar with his background, with his permission, I'll simply summarize it by saying that as well as a past president of the BCS and a past chairman of the Engineering Council, in his full-time career, he spent a long time with IBM, where he was responsible for various technological developments and senior management positions, ending up as a director of IBM UK Limited. He then went on to become the Chief Scientific Advisor to the Cabinet Office, after which he was knighted. He is now in retirement, funny sort of retirement, but the amount that he's doing. And among other things, but principally, he is the chairman of the Rothschild Ventures Limited. Go back a while, his first position after leaving university was to be a member of the development team for Pegasus. So he knows what he's talking about, whereas I'm ignorant. So without any more ado, Sir John Fair.
Thank you very much, Alan. Ladies and gentlemen, it really is a great privilege for me to be given the opportunity to chair this afternoon's session. I feel rather humble in many ways. I was a very junior engineer in 1954 when I graduated from Tech, now UMIST, and joined the Pegasus team in Manchester Street. I accepted the job that Bill Elliott offered me, not because I had any vision of becoming part of the emerging computer industry, but because my wife-to-be worked around the corner. And it was a happy coincidence of events, I have to say. I enjoyed Manchester Street and then Portland Place enormously, until Ferranti invited me, together with a chap called New Zealander called John Howard, who had worked on the torsional delay lines. My job on Pegasus was the design of the magnetorestricted delay lines, and I worked for one of the best engineers I've had the good fortune to know, called Charles Owen, and I learned more about engineering from Charles Owen than at any university, I have to say. And John Howard and I were invited by Ferranti to go to the United States because Ferranti had hopes of selling that technology to the United States industry. And that's how I ended up abandoning ship and joining IBM in the United States after 2 years over there. But it's a great honor and a privilege. Many of the people who are here, who participated in the design of Stretch, were already, how can I say, big cheeses. They were all very senior to me. That's why I feel so humble when I was standing in front of you today, as I was a very junior engineer. And so I really reiterate my opening remarks. It's a great privilege to be with you. 47 years ago, 1954, it's a long time, and to see a Pegasus working today, I think it brought a lump to my throat and tears to my eyes. It's a great achievement, but more about that later. Our first speaker, what's the problem?
We better without my mic altogether. I don't have PA electronics.
Is that better? Somebody needs to record it, I think, John. Is that not right? Right. Well, our first speaker is Simon Lavington. Simon is responsible for organising the seminar today, and we're all most grateful to him. Where is he? There he is. He's written the booklet, which many of you may have seen, describing Pegasus and its design. And we really look forward to your introduction, Simon. Simon graduated as an electrical engineer from Manchester in '62, and he joined Tom Kilburn's computer design group. After that, in 1981, he started his own research group, and shortly after, in 1986, became professor of computer science at the University of Essex, where he still is. And his publications cover a wide variety of subjects from high-performance computer architectures, speech recognition, data mining, video over the internet, and the history of computers. He's probably made more money out of the history of computers, he tells me, than out of his technical papers. Simon? Let's
John.
Leave the mic. Turn it on.
I think we're recording, so let's see if I can speak without rumbling. A brief introduction, 10 minutes, and let me start with the timescale of what we're going to talk about today. Two firms are involved in this slide, Elliott Brothers Limited and Ferranti Limited, and we're looking at a 10-year period, roughly 1956 to 60. There are several machines on this slide, and I've tried to indicate in terms of these different colours the hardware or design activity for each machine. In amongst this is the effect of NRDC, National Research Development Corporation, and its various contracts, and more of those later. Of the machines in this slide, the 152 and 153 projects at Elliott's Boreham Wood Lab were special purpose computers for naval fire control. The other computers, namely Elliott, the Elliott Nicholas, an in-house computer, the 401, and of course Pegasus, were all general purpose computers. The Pegasus story starts roughly in September of 1950, when NRDC gave a contract to the computer division at Boreham Wood for the investigation of their packaging techniques, printed circuit, early printed circuit and packaging techniques to digital computers. And that led to a demonstrator called SNARC, short nickel line accumulating register computer, which was demonstrated in early 1952. Meanwhile, the theory group at Boreham Wood had built their own in-house computer called Nicholas, which is a fascinating but different story. The further contracts with Elliott's led to the production of the 401 computer, which first ran the program in March of 1953, and by March of 1954 was moved to the Rothamsted agricultural research establishment. In the middle of this period, namely by early or mid-1953, a move of personnel had occurred at Elliott Brothers, about which more later. Partly due to that move in personnel, and partly for other reasons, we find that the NRDC contracts moved to Ferranti Limited and produced a project that at first was called the Ferranti Packaged Computer, FPC-1, the name of which was afterwards changed to Pegasus. Pegasus first ran a program in October 1955. That was without the drum at that time. The drum was operational in about March of 56. And from April 56, that first Pegasus was doing useful work for paying customers. On this slide, where I've drawn these plus lines, just about visible, that indicates the machines that went into production. And by October of 1962, 40 Pegasus machines had been delivered. You can see that as far as Ferranti is concerned, this activity was interleaved with other computers, but we're not here to discuss those. So let me turn to the somewhat difficult question of personnel movement. And I hope to show by a few photographs the sort of influences that went from Borehamwood to Ferranti. We start off with a picture of the computing division at Borehamwood in about late 1952 or early 1953. This is an interesting picture because one prominent front row person is actually not in the computing division. This is Charles Owen, who comes from the circuits lab. And one might deduce there's a certain political reason for having him in this particular photograph. Other people who were at Borehamwood at the time, but not shown in the photograph, but whose names will occur later on this afternoon, are Hugh Devenold and George Felton, both in the theory lab. And if you remember, I said that it was the theory lab that produced that in-house computer, Nicholas. It's interesting to see which of those people played a prominent part in the design and implementation of the 401. Of course, mentioning names is always a bit tricky, but taking the criterion of inclusion of a person's name as author of a published paper or principal company report, then one might hazard a guess that the following people were key to the 401 design. Under the group leadership of Harry Carpenter, there was Lawrence Clark, Anderson Johnson, Berwick Stallworthy, and Norman Muchmore. And in the theory lab, Hugh Devenold. Now I mention those names because if history had been otherwise, it may well have been those people who went on to produce the machine that we're now talking about today. What in fact happened is that there was a sort of bifurcation, a change in management strategy that led to the resignation of the head of the Borehamwood lab and also Bill Elliott, the leader of the computing division. And the people hatched in red by the end of 1954 had left Borehamwood. Harry Carpenter, who has measles in this slide, I dotted because at first he went to be a consultant, whereas the other people who were hatched in ended up in Ferranti. And one might imagine the dismay of the people left behind, these people who designed the 401, to see their front line disappear. Happily, under the leadership of Anderson Johnston, these people went on to design the Elliott 405, the Elliott 803, and other successful machines. And it's worth saying that by mid-1962, 30 Elliott 405s had been delivered, and by the same year, 76 Elliott 803s had been delivered. So what of Ferranti, where the people hatched in red ended up? Here's a photograph of Ferranti's London computer lab in the summer of 1956. A photograph taken in Regent's Park of essentially Bill Elliott's team. Again, there's a certain sort of, I would perhaps say, political understanding that has to, you have had to appreciate who is and who isn't in this photograph. There are 103 people shown. Most of the people shown had something to do with Pegasus. A subset had not, under Peter Dorey, there was a group working on Ferranti's defence contracts. Significantly, for me at any rate, as somebody who attempts to understand this time, nobody in what we might call the software or applications side of the Pegasus team is shown in the photograph. Particularly people like George Felton, who reported to Bernard Swan, thank you, are not shown. And particularly also, none of the NRDC people are shown, and most particularly the person who stands up, as I think we shall see later, as making a seminal contribution to Pegasus, named Christopher Strachey. He is not shown in that photograph. But with those provisos, one might remark on the dozen or so people in this photograph who might be classed as principal contributors to this design. That is to say, people whose names might be expected to appear on published paper. And I've selected this dozen or so names that I think one might look to for design contribution, and they include people like Charles Owen, Brian Maudsley, Ian Merry, Hugh Devenald, John Fairclough, Ted Brownholmes, and a few others. And it's interesting to then overlay in red a reminder of the three of those dozen or so people who migrated from Boreham Wood. And they include Bill Elliott himself, Charles Owen, and Hugh Devenald. Well, enough of that. They were difficult times politically for many of the players involved, but I think that gives you some sense of the interaction between the two companies. That's people. How about places? This is 21 Portland Place, an elegant building near Oxford Street. One of the first inhabitants was General Sir Henry Clinton, who in 1778 was the Commander-in-Chief of British forces in America, but that's another story. Ferranti's London Computer Centre was housed in these elegant premises. And something that I find interesting, the first Pegasus was assembled in the first floor room of this elegant house. That is to say, before Ferranti at Manchester, the West Gorton factory, got into production of the other following 39 Pegasi, the first one existed in the elegant house. Besides the first Pegasus, by 1960 there were something like 60 staff in this building, occupied in the following four areas, which I think give an indication of the activity that Ferranti brought to customer support. First of all, these staff were running a computing service for paying customers on the Ferranti machine. Secondly, they were holding demonstrations to prospective Pegasus sales prospects. Thirdly, they were running regular two-week programming courses, and I guess George might say something about those later. And finally, there was the development, documentation, and dissemination process for the extensive Pegasus software library. Finally, by way of introduction, let me show you an attempt to explain the architecture of Pegasus in respect of operand fetching in terms of modern parlance. This is a diagram that I drew myself when I was trying to understand Pegasus, and when I'd completed the diagram, I was amazed at the elegant nature of the architecture and the fact that the diagram I'd drawn was probably identical to the ones that I would draw for my first year students when explaining to them a general register set architecture. Specifically, in red here we have the arithmetic and logic unit, which interestingly in Pegasus was called the mill, resurrecting the terminology used by Charles Babbage. I think this is the earliest electronic computer to use the term mill. I know it was used by Freund in the ICL in the 1900s as well. There's people, apparently it's used earlier. I'm sure George will tell us about that in a moment. The ALU has on its two input highways, buses, a set of general registers, the accumulators, and a cache, which we would call nowadays a RAM cache, for code and data. These were the nickel delay lines, and then the backing store, the magnetic store of the drum there, and input and output, memory mapped input and output. I'm sure further speakers will elaborate on this diagram. To my mind, as I say, elegance is the key word here, and it seems to me, I looked for comment from others who were actually there at the time, it seems to me that what we're looking at there is the genius of Christopher Strachey. Well, that's all I have to say by way of introduction.
Thank you very much.
John?
Does anyone have any questions for Morris?
One correct recollection I have, tell me perhaps I'm wrong. The Elliott's first proposal was to have a core memory with a drum as a backup. He was disappointed when he come to that is there any evidence in the surviving records of that?
That's very interesting. I'd not known that. We're talking about 1954 then. It's a proposal for the FPC-1, was it?
Well, perhaps the dates don't make the core memory at that time unlikely.
Yeah. Well, I know that in May 54, the Manchester Meg had run a first program, and that was CRT storage, whereas Mercury substituted cores, didn't it, for...
Perhaps quite wrong. Perhaps it's
Yeah.
reservation storage.
I would like to hear from others on that. It seems to be a little bit early for cores. Yes.
One of your slides showed several sort of precursor computers to Pegasus. One strikes something being snap-down based. That's it, the Manchester Mark I. Did that have any contribution to all the other computers? Did the Manchester Mark I really contribute to Pegasus?
No, indeed. That's why I really didn't mention it, but I just wanted to show that Pegasus was interleaved with other Manchester activity. And although I didn't say it, those who know will recognise the two cultures, the Manchester and the London culture, and Pegasus was firmly in the London culture.
So think from the anti culture, which is something quite different.
Could I point out that Nicholas, although you have shown it with a very short time bar, actually continued to operate a computing service at Bournemouth until 1958. Very successful.
Yes, thank you. I should have said that the plus signs only indicate production machines. Nicholas indeed successfully, as you say, and the 401 until I think 1965 at Rothamsted. Yeah.
I'm afraid I'm going to have to be a tough chairman. If we don't finish by about 10 to 6, we're all going to get locked in, I think, or at least some of you are. So I fear we must move on. Thank you very much, Simon. Our next speaker is Hugh Devenant, and I think Simon has introduced him already. Hugh was held in awe by some of us junior engineers, I remember at the time, because he really understood how this machine worked. And he's going to tell us more about the design. Hugh.
Say anything, John? Switch here, it's all right. Seems the thing to put one's name up first. Well, good afternoon, ladies and gentlemen. I am pleased and indeed fortunate to be here to speak to you today. Some of those, perhaps more qualified than myself, are no longer with us. I refer, of course, to Bill Elliott himself, who headed up the Pegasus team, to Christopher Strachey, who was the consultant architect, Charles Owen, whose electronics were outstanding, Brian Maudsley, who seemed to bring a common sense approach to mechanical engineering and did great work in the machine. And I think one should mention Bernard Swan as the Ferranti computer sales manager, who had something to say, and who I think, with George Felton, who's here today, devised the name Pegasus. I'm not quite sure if that's right, George. Yes, right. I hope you, or most of you, have got hold of Simon's book, The Pegasus Story. It will say more about Pegasus and its background and indeed its future than one can say in a short speech this afternoon. I like the idea of the Pegasus story. It seems to sum up a film script. Philadelphia story, love story. I wonder if Simon is selling the film rights, and who would play Bill Elliott? I hope to refresh the memories of some of you here today, probably some of you with far better memories than myself. And for those few younger people in the audience, I hope we may, during the afternoon, produce some sense of history of the computer business. My credentials, which were slightly exaggerated originally, I can't think I actually did much of the design of 401. I certainly did some commissioning of it. And then I moved on to Ferranti at the tail end of 1953. I think I was the first to join Bill Elliott. And I headed up for several years a logical design team, both for Pegasus and for the later machine, Perseus. If I can find the right slide. I intend this afternoon to really cover just those subjects, the Ferranti package computer number 1, something about packaging, and the design aims as I set them out in an in-house Ferranti journal in 1956. There's already been some talk about the F for Ferranti, and I don't want to open that up. It might well have been another company, but it was Ferranti, and personally I was very pleased it was, and I think most of us who worked on the Pegasus machine probably enjoyed the best times in our career, because we were convinced that, like the mythical Pegasus, you could climb to the skies and really have the best machine possible. The PC stood for packaged computer. Bill Elliott was an enthusiast for packages and had, with others, done a lot of development work at Elliott Brothers before he broke away. A package is really just an assembly of electronic elements, which with other packages plug into a larger assembly to become ultimately the full electronics of the computer. To make the thing successful, you need to have a very few packages used a large number of times, and in Pegasus, some 86% of all the packages were in the logic types and the nickel lines, and then there were some more special ones for handling drum input-output and the clock and reset. In all, 444, which seems a rather magical number. The packages themselves, for those interested in the logic of it, those, and I know those people here who will recall this very vividly, those were the 5 main logical packages, where the squares are AND gates, the Ds are delays, the cross bars are inverters, and the bottom line are cathode followers to boost the signals. with those devices, we were able to build up the full description of the machine. That is not exactly a typical package. It's typical in its size, and they all had 2 or 3 double triode valves. This is the delay line that John Fairclough developed. And at the bottom we have the 32-way plug-in socket that went into the frame. The component side was typically like that. I haven't been able to find in the references an exact size for that. You can see them upstairs. I guess it's about 5 inches across and about 10 inches deep. The handle is integral with the base plate holding the components. It acts as a shield for the valves, and when assembled into the computer, you can see that a line of packages, the shoulders, as it were, of the packages form a heat shield between the valves and the components behind, and then some forced air comes from a fan at the bottom and exhausts through the top. For the basic Pegasus, we managed without air conditioning. The one upstairs is a larger size and has got a built-in refrigeration system. On the control desk are the 2 paper tape readers on the left for input, the teleprinter for output, and the paper tape punch. There's a Ferranti clock. At that time, Ferranti not only made computers, they made television sets and fires and clocks. And I'm pleased to see upstairs the original clock is still working. I think that's why they gave them up. They were too expensive to make. And there was a control panel there, and slightly hidden in that picture, the hand keys, which were the way of bootstrapping into the system when it was first put up. Because I've got it to hand, I'll show you the production line at Westbourne with the Pegasus machines on the right, and I think it's the Mercury machines at the back. It was quite an impressive sight, and tucked away around the corner here, there was a thing called 10 Bay, where I guess about 100 girls were busy wiring the individual packages before sending them across tested to the commissioning bay. But a bit more of that later. Oh, there's another, I've got another slide somewhere I'd like to share. Oh, yes. Just as an indication of the logic design, that, oh, upside down. That is an adder. It occupies, well, there are 3 different sorts of packages there, but in total it's about 2.5 packages, so that the total machine was about 200 times that in complexity, and the logic diagrams extended to 200 times that size. I was, myself and my team, we managed to interpret Straight-Sheet's ideas and order code into that form so that when the package positions were determined and the pin numbers added, the production people could manufacture a machine. I'd just like to say just a word about the logic diagrams. I don't know whether, but it doesn't really matter whether it is or not. Ian Merry, in a somewhat similar seminar about 6 years ago, spoke of the logic design and said that despite the lectures given by the logical design team, he was unable to understand the various cycles of operation within the machine. I'm not sure whether that was a comment praising the logical designers for being so clever or criticizing us for being so abstruse. But we understood it, and I have evidence from other people who attended those lectures that they understood it too. And Peter Hunt, who was perhaps one of the best of the early programmers on Pegasus, obtained a set of the logic diagrams and thought they were very beautiful. In fact, if there had been a Turner Prize around at the time, they could well have been entered for it because they were very good. And I hope there is a set around somewhere here today. But Peter took them home, papered his downstairs loo with them, and therefore by daily study probably got to understand them completely. There seems no doubt that packages have many advantages over other methods of design, although there was quite criticism of it in the 50s, primarily because of poor private socket contacts, which Maudsley overcame by some good engineering, and also by the fear that there might be a lot of redundancy in the resulting machine. We claimed that there were 10% redundancy in diodes and a few resistors, and that the total cost of redundancy was £150, which was, I guess, about 1% of the manufacturing cost. They have obvious advantages in production and in commissioning, because there's something which is ready tested, so that most of what you're commissioning is ready tested. There have been occasions when a package has slipped through the testing procedure, and I was reminded recently of one example by an engineer who's present here today, Douglas Hogg, that in commissioning the magnetic tape later in Portland Place, one rogue package, self-destructed on being plugged in, blew fuses, stopped the alternator in the basement, and Douglas was so cross that he pulled it out, stamped on it, and buried it in the false floor. And presumably someone found it a little later. But generally speaking, the pre-testing was good, and the result meant that the commissioning was good. And then when we come to maintenance, the maintenance programs can, in general, cater fault down to a few packages. Each of the packages has a series of monitor points on the front, and by quick monitoring of the suspected packages, one can identify which one is wrong and quite quickly change it. So I think we proved beyond doubt that at that time the package concept was good. It was called FPC-1 because we thought we could make some more with the same packages. In the result, there was only one further machine, the Perseus, and I think as we mentioned earlier, there were only 2 models made. A little ironically, it was probably the only multi-radix machine ever built and sold to a decimal currency. So we weren't able to take advantage of the pounds, shillings and pence, and I don't think the Swedes would want to add up in tons, hundredweights and quarters. But nevertheless, it was an interesting machine in that way. The design aims, which I had up earlier, included being in the medium price range. And I think in 1955-56, that was meant to be about £30,000. There were some arguments about it with NRDC, but let's take that as a round figure, which I suppose with inflation would be about £1.5 million today. So that the investment for a company in 1955 of 30,000 in a piece of office equipment was quite something. Mind you, as in use of technology itself, as I need hardly tell you, inflation has been completely flattened by the improvement in technology. So you can go out into the high street today and buy probably for £1,000 a machine with a clock rate 1,000 times faster than Pegasus, with probably 1 million times more store, with facilities that even the science fiction writer in 1953 would have dreamt of, and all that for £1,000. I guess that there's probably more electronic logic in your mobile phone than there is in Pegasus. That's another story. So it was medium price range. And Burmese Swan thought that if someone was going to spend this amount of money on a piece of office equipment, it needed to look good. So this prompted Brian Maudsley, the mechanical man, to go to Mulliners, the Rolls-Royce coach builders, to see what they could do. And the result, which if you haven't seen it before, or if you haven't seen it for a long time, you can see upstairs today, is a rather beautiful, rounded cabinet work, where it was reputed 10 coats of what was called Valentine's Special Lavender No. 2 paint was applied with delicate rubbing down between each coat, and the result certainly looked worth £30,000.
Correction, it was 14 coats.
14, I beg your pardon, yes. There are two stories about that. One I like was that later on, when the London lab migrated to Bracknell and we were building the Perseus machine, as I mentioned, with the same technology and so on, Mulliners turned up with the cabinet work in an open lorry, which was probably the only lorry in the world driven by a Rolls-Royce engine with a distinctive radiator grille. It really was worth seeing. The other story is perhaps not quite so pleasant. Brian Maudsley, who was very proud of these cabinets, went one day to the Samus research labs of Whiteleaf, where we were collaborating with Powers over a card to tape converter, and looked at these inferior cabinets that they were using there, got a penny out of his pocket and ran it down the cabinet and said, "Look, what scratches. Wouldn't happen on Pegasus." But I don't suggest you go out and see the first Rolls Royce, try it. They may not have gone to Mulliners. Where are we? The next design aim was the machine should be easy to produce, and I think I've covered that, and that it should be extremely reliable. Now, we're talking here about 1955, when some machines had to run longest programs several times and only accept results when two sets agreed, so that we were looking for something far better than that. And with the circuits that Charles Owen designed, and with the plugs and sockets that overcame the problems that Brian Maudsley designed, we thought we had a very good basic system there. There were other aids to reliability, as I mentioned, the pre-testing of the packages, the slow run-up of the heaters on the valves so that they wouldn't suffer too much, the expulsion of heat that I mentioned too, so that we were okay there. A conservative clock rate, we had 333 kilohertz, which was really, there were plenty of 1 megahertz machines around at the time, but we felt it was a good conservative figure to use, and it fitted in well with the drum design and the delay lines. And then pre-shift engineering test runs would take place with reduced power supply voltages to try and pick up any incipient faults that might occur. So yes, we had a reliable machine, and somewhere here I've got some figures to prove it. Somewhere. These figures refer to Pegasus number 4. So I didn't have many to choose from in picking these figures to put into the Parenti Journal. There were only 4 machines operating at the time, and this was for a period of 8 weeks up to March 1957, and this machine was only installed in November 1956. So within 6 months, it was behaving in that way. We included in useful time anything due to operators' errors, but fault time and downtime and fault repair time obviously contributed to a poor performance. But we had those figures. There is a slight exaggeration there. When I redid the arithmetic recently, that should have said 98.6. It wasn't quite over 99, but very close to it. So I think we could say that we had a very reliable machine, and one which was an eye-opener to the computer industry generally at that time. The final point, and perhaps one which is most important in many ways, and that was that it should be easy to use. Now, this is a rather subjective criterion. I think there were people working on Mark I and Mark I Star at Manchester who thought that was an easier machine to program than Pegasus. I would prefer to say that, oh, and I was going to say too, sorry George, that there were programmers working on Pegasus who would have found any machine easy. Such was their quality. I lost my thread. I would prefer to say that we wanted a design which was not only easy to use, but was effective in getting the best performance out of the system. And I think there's no doubt that the architecture that Strachey laid down, and it was contributed to by other people. I remember, for example, Ted Brownholtz, who was one of the logic designers at the time, saying that standing on Didcot Station one morning, he thought what a good idea it would be to have a counter and a modifier in the same register, which hadn't at that time occurred to anyone else, I believe, and indeed that got incorporated into the instruction code. The other thing, of course, is that when you're looking for ease of programming and indeed effectiveness, there's a bit of a battle between people wanting facilities and those wanting to keep the costs down. And there certainly were some quite good discussions, arguments between Ben Elliott and Strachey, but I think the compromise result was very good. The main features, I think, which contribute to this, and I'm sure George Felton will be saying more about this later, the main features are the two-level store, which was shown by Simon earlier, and if I can put that slide up again. Combination of a backing store and what I gather now is called a RAM cache. And coupled with that, the fact that the multiple accumulators were addressable in the same group as the cache, and that there were good instructions for transferring information between the drum and the store, what we might call immediate access store, meant that programmers could work within that, in fact had to work within the RAM cache store. And bear in mind that the size that we're talking of here is something like 55 words here and 4,000 in the drum, word being something like 5 bytes, 4 or 5 bytes. It was remarkable that anyone could do anything, but people did everything. And again, if I may say something about George Felton, he did, for some 6 months, using Pegasus, hold the world record for the number of places in pi. This was 10,000, taking over from someone with a much bigger machine who'd only managed 3,000, and holding it for 6 months until someone with an even bigger machine got it up to 16,000. It's remarkable what you can do. The other program I remember was that Strachey was writing love letters with it, with a random. I will stop. We need to move on. Right. Well, there was more I was going to say, particularly about the future, but I'll stop, and no doubt people can follow on from that later.
Good, thank you very much. Anyone bursting with a question?
Well, it's a comment rather than a question. The one thing you didn't mention, which actually helped the program, was like being a Pegasus, worked at night, and the machine went wrong. But by looking at the logic diagrams, the way they were numbered, and parts of those were numbered, you knew exactly where you would put a test. Because the numbering related to the row and day and test point on the machine. And we could even pick out the right spare package with the raw light colour codes. You could see what that was. And we looked at one with the same colour, but then you put it back, put the spare one in there, and the machine worked again.
Thank you.
Thank you very much.
Thank you. I think the modularity in the design of Pegasus survives even till today.
Yes.
And the structure of, we call today, mother cards, daughter cards, etc., that really did make a valuable contribution.
Hugh, would you like to say a few words about phase 7 and 8, which were an attempt to convert it into a data processing machine?
Sorry,
Would you like to say something about phase 7 and 8, which were an attempt to convert Pegasus into a data processing machine, and then it was overtaken by a riot?
Could I say, Joe, there's a discussion session at the end.
Yes, general questions like that, I think we may
Thank you, Chairman. Thank you,
Let's move on. I think it's interesting to note that the hardware and software were managed independently. Software by marketing, and hardware, as we all know, by Bill Elliott. And one wondered whether the twain might meet from time to time. We were fortunate in having George in charge of the software, and George, who are now going to tell us about it. George worked originally in the RAF on radar, and then he, as you heard, joined Elliott Brothers and was responsible for Nicholas' programming system. And then he went on to join Ferranti and subsequently ICT, ICL, as we all know. George, it's a great pleasure to welcome you here today.
Good afternoon, ladies and gentlemen. Yes, this slide, I must admit that when I saw this diagram, I was completely baffled. Somehow or other, we programmers never thought of a machine like that. The RAM cache is a modern word, of course. 50 years later, it doesn't seem to be what we had in mind. This is a historical occasion, so I'd really rather use some of the historical terms, which I hope I can explain should anyone fail to understand them. Mention was made of the name of the machine, the Ferranti Packaged Computer Number 1, FPC. So when somebody thought that we ought to have a better name for it, somebody pointed out that if we found a name beginning with P, then, like Pegasus for instance, then it would be the Ferranti Pegasus Computer, which would mean you wouldn't have to abandon the old name. And the name...
Bill Elliott happy.
Yes. Bill was very happy, I think. But several of us thought of this name at about the same time, and it seemed to please everyone. And later on we had Perseus and a few others, I think, in the same vein. This is an original copy here, introducing Pegasus, the Ferranti Packaged Computer Number 1, advanced copy, January 1955. I'll leave a few things here if people want to look at them. Oh, I ought to put up this thing to start with all the time, sorry. My interest in computing started before the war, actually. I went to Paris in 1937 to see the French great exhibition there, international exhibition, and I noticed around the inside of a dome there were 707 figures of pi, calculated by Mr. Shanks in 1880 or thereabouts. And I wondered how on earth he could calculate such a number, because I was only 17 at the time, and I didn't know really how to do it. So I made it my business to find out. Quite interesting, really. And then I went into the armed services during the war and worked on radar. So when I emerged after the war, I understood the radar circuits and things like that very well. Now when I went back to Cambridge, I found that they were building one of the first 3 computers in the UK there. And they were using circuits I knew a lot about on radar to build this wonderful engine. And it eventually worked in April '49, a little bit behind the baby machine in Manchester, but I would claim that EDSAC was a lot more programmable than the original baby. It was designed to be a machine on which a computing service is going to be operated in the university. And then, when I went down from Cambridge, I went to Elliott Brothers, and I worked on an analog computer for a time, rather against the grain, I must say. I felt my heart was in digital. And then, lo and behold, Nicholas materialized, designed, I'm told, by Charles Owen during a 3-week period in which he was absent from work because of having flu. And when he came back, he had 1 sheet of paper on which was the logical diagram for this complete digital computer, with magnetostrictive delay lines. And they were very anxious at that time to test the idea of these delay lines, because the potential was enormous. The delay lines then in use were mainly mercury delay lines, which involved a lot of precision engineering. But the nickel lines were so cheap to make that they really were a great advantage. And Nicholas derived its name, of course, from the nickel delay lines. And my wife and I both wrote programs for this machine, including the initial orders on it. And indeed, my wife gave up programming in 1953 so that we could start a family, and we called our first son Nicholas, after the computer. And the influence goes on a bit because the Nicholas was a very simple machine from the programmer's point of view. 1,024 words was the memory, and that was it. No backing drum. Paper tape in and out. Very straightforward, but very limited set of instructions. And you could follow the logical diagram because they were all on this 1 sheet of paper. And we used to start up the machine in the morning, and it wouldn't work, but we somehow or other managed to wheel up the oscilloscope and find the package. Anyway, it was great fun. So I moved to Ferranti in '54, the end of '54, and Hugh Ross, who I don't think is here today. Yes? Oh, hello, Hugh. Hugh very kindly slipped me a few advance pieces of paper with the order code of Pegasus on, things like that, and I was bowled over by its elegance. I think you would agree that it's a very elegant machine, and as a mathematician, elegance is of great importance. Well, here we have another diagram of the fast store, or the RAM cache, as seems to be the official wording nowadays. These are the decimal addresses of all the words, all the registers in the computing store. You can see the accumulators at the top. They were always in the forefront of the programmer's thinking. What do we put in these very precious accumulators? Every instruction, bar a few, would operate on the accumulators. And they were very valuable. accumulator 0 always had naught in it. It was just a wire going down to minus 10 volts or something, I believe. 8 to 14 not assigned. Then 15 was the hand switches. This was very useful. 16 and 17 provided for input and output. And then there were 3 useful constants there. 32, 33, 34, 4 useful constants, I should say. 35. 2 to the minus 13 may seem an arbitrary value, 2 to the minus 10, but that was where the modifier was placed in the accumulators. And the 64 to 111 we referred to as 0.0 to 5.7. We wrote those in octal. At least we never thought of it as octal, but that's the way it was. So this shows the way we always used to think of them. The accumulators at the top there, the special registers largely for input, output and things of that kind, and underneath the ordinary registers arranged in these 6 blocks of 8 each. This was 48 words here. Add the 7 accumulators, you've got 55, and that was all you worked in. All the work was done there. However, we had behind us the magnetic drum with its 4,000 or 7,000 words, depending which model you've got. And the initial orders, which were a vital part of the machine, were stored permanently in this drum. You could think of the drum as being made up of individual words. You could actually address the drum one word at a time. You could write to one word, you could write one word to the drum, or you could read one word. But that was a bit unusual. We usually tried to transfer a block at a time, that is 8 words. We would read a block from the drum and transfer it to one of these blocks of ordinary registers, for instance. Or even to block 7, which was the accumulators. It provided a very elegant system for addressing anyway. And there's another unit which nobody's mentioned so far, the overflow indicator here, OVR. This was set whenever the arithmetical operations produced an unreliable answer due to overflow. And we could detect this fact. I think it must have been one of the very first machines to put this in. Correct me if I'm wrong, somebody, but I'd certainly not come across it before. The order code, as we used to call it, nowadays instruction format, as the translation provided by Simon. Orders, of course, the word's a little ambiguous, but that's how we thought of it. There were just a few parts in the order. The main part was the function, of course, the operation code, 6 binary digits. There were 2 addresses, N and X. X normally referred to one of the accumulators, and N referred to anywhere in the computing store. It could be an accumulator, or it could be one of the ordinary registers. Or sometimes it was just a number. And M is the modifier, the 3 binary digits which specify which accumulator modifier is to be used to modify the address in the instruction. Of course, most of the time the instructions were not modified, so M was 0, and accumulator 0, you remember, didn't have anything in it, so the instruction was unmodified. It saved a lot of trouble. The explanation here applies to the basic instructions in the machine. Little x denotes an accumulator, and x dashed indicates the number in the accumulator after the instruction has been obeyed. So here we have that the number in the accumulator afterwards is equal to the number before the operation applied with some function phi in conjunction with n, which might refer to another accumulator or to an ordinary register, or might be just a number. And n dashed with some of the operations. We actually wrote the answer into the ordinary register, and sometimes there was a constant. Anyway, I'll show you the order code complete. These are all the functions that we had access to, and these ones on the left and the one at the top right group we use most. So here's an enlarged drawing of most of them anyway. These are the simple instructions. You see, the first one copies a number from a register into an accumulator. And down here we have the exact converse, takes the accumulator content into the register. Here we have the transfer with adding to what's in the accumulator, and O3 is subtracting it from the accumulator, O4 is subtracting it the other way around, O2 is putting a negative in, and so on. X5 is ANDing the two operations logically, and O6 is what we used to call a not equivalent operation. We always wrote it as 3 lines crossed out, but there you change the units in a well-known way. These are exactly parallel, but the answer is always in the ordinary register, not necessarily an accumulator. And these again are parallel, but C here is simply a small number which you write into the order. And you can see those 3 groups of instructions work. They're very straightforward, and you can work with them very easily. Group 2 is concerned with multiplication and division. The basic one is 2, 0. You multiply the number in a register by the number in an accumulator, and this of course gives you a double length product, and this will appear in accumulators 6 and 7. Each accumulator at each register holds 39 binary digits from the programmer's point of view. The most significant digit is a sign digit. Number ranges from -1 inclusive to +1 exclusive in steps of 2 to the minus 38. But here we have a double length one, and you have a sign digit, and actually you have a spare in the middle because of the way the thing works. The sign bit in accumulator 7 was always end up as 0. 21 was rounded multiplication, which ended up in accumulator 6. 22 is a very useful instruction, multiply and add, and that was a double length addition into 6 and 7. 23, justify. This was very useful for double length arithmetic, or quadruple length, or multiple length. When you're working with pi, you have to use a very, very large number, and things like justify are exceptionally valuable. Roughly speaking, if you do a double length addition, you can add together the 2 top halves of the number in accumulator 6 and the 2 bottom halves of the number into accumulator 7, and then you just obey a 2-3 instruction, and it will put that double length number into standard form, allowing for have it perhaps overflowing in accumulator 7, or changing the sign and what have you. Very simple, useful instruction. 3 divide instructions. The first one is the basic one, which takes a double length dividend, divides it by a single length divisor, and puts the quotient into accumulator 6 and the remainder into accumulator 7. These mathematical operations were very precisely defined by Christopher Strachey, who was a first-class mathematician. They were very precisely defined by terms which any mathematician could understand with great precision. You knew exactly what was going to happen when a piece of arithmetic happened. And since I've been playing with other machines, earlier ones, I was overjoyed to discover that one knew exactly what happened here. Well, we have these double-length dividend, which gives you a single-length quotient. 25 gives you the rounded quotient and the corresponding remainder, and 26 gives you just the quotient. And then group 5 is concerned with shifts. Arithmetic shifts, where you may get overflow. 51 is a single length downshift with rounding. 52, a logical shift where there's no possibility of overflow because you ignore it. 53 and 54, sorry, 53 is double length, no it isn't. It's a logical shift down, yes. And then 54, 55, and 56 are the, sorry, 54 and 55 are the double length up and down, unrounded, and this one is, this was the floating point instruction. It's a very nice one, this. Normalize a floating point number. You could have a double length operand for your floating point. The argument of the floating point number would be in accumulators 6 and 7. The exponent would be in one of the other accumulators. And when you obey the 56 order, it does everything just right. You end up with a standardized floating point number in 2 places, and you can pack it up in any way you require. Another important set of instructions are what we used to call the jumps, transfers of control. Jump if x equals 0. So an order there would be if the content of a specified accumulator is 0, then you obey next the instruction in the register you specify, and it could be either of the words, in either of the commands in that register. Converse is jump if x is not 0, jump if x is greater than or equal to 0, jump if negative, jump if overflow is clear, jump if overflow is set. Unit modifier. These are very clever instructions which Hugh Devenant mentioned as having been devised by Ted Brownholtz, who unfortunately can't be here today. I remember him and Hugh Devenant with great respect and affection. They were delightful people to work with. Now, the 66 instruction adds 1 to the modifier in an accumulator, and if the last 3 bits of the modified address are 0, sorry, if it's not 0, then the jump occurs. If it is 0, you continue with the next instruction. This makes the use of a 2-level store really practical and easy, and almost as easy as having a single-level store to work in. I'll show you shortly how we use that one. 67 decrements a counter at the least significant end of the accumulator and jumps if it's not 0. Those are all very carefully thought out commands. The 7 group, reading and writing to and from the drum, a single word at a time, involving accumulator 1 only, and 72, 73, block reading and writing, and 74 selects between various input and output devices. Now, I'd like to explain, if I may, the operation of the 2-level store. And I've got 3 charts here to show this. The first one shows the contents of an accumulator in graphical form. You've got to imagine this is a binary number. The sign bit is at the top end, and the 39th bit is the least significant one. After the sign bit, which plays no part in this procedure, you get a 13-bit modifier, which is made up of a block number and a position number within the block. And following that, you've got a counter of up to 25 digits, but that was pretty generous, really. But it's a very interesting idea to have these 2 numbers in one accumulator. Very useful. Now, the various instructions are modified in different ways. This is something to remember. Whose phone is that? Hi. The ordinary arithmetical operations, which manipulated numbers within the computing store, were modified by adding only the position part of the modifier. So you could step through a block in the ordinary register, starting at any place you liked, and step forward through that. And when you got to the end of the block, then you could detect that and something would happen. That involved all these arithmetical orders, including the multiply, you notice. Here's an example here, 4.02005, and if 5 contains 51.6, then the 6 is added to the 0 to produce 6. That's a surprise, isn't it? And the block number is not affected, so the modified one is just like that. Another little step involves the transfers to and from the drum, the backing store, the main store as we used to call it. We had a block read and a block write. In this case, what is apparently the address of the accumulator is in fact the block number within the computing store. So that block 4, U4 we used to call it, U for computing. U4 was 4.0, 4.1 and so on, down to 4.7. And 30, this is a decimal address on the main store, the drum. So that would read block 30 from the drum into U4 in the computing store. This is a similar operation, writing into the main store. Now if we modify these two, then only the block number takes part in the modification. So if you write this instruction here, the block part of modifier in 5 gets added to the block number here, 30. And if you've got 51.6 there, then 51 will get added to 30. So the instruction that's actually obeyed is that, which causes block 81 from the drum to be read in and put into 4.0, 4.1, 4.2 and so on. Very straightforward. And it's very important to notice that you can use the same modifier in these block transfer commands and also in the arithmetical commands. The two component parts of the modifier are split out. So here we have reading, if we have B51.6 in the modifier position in accumulator 5, then this command will copy block 51 from the main store into block 4 in the computing store. This instruction, which is extracts a number from that block and puts it into accumulator 2, and it will be modified by the same modifier using the position number. Now this is how we use it, and this is really the crunch point for programming Pegasus in a lot of ways. This as a simple example. Ignore the first thing. This is just a way of writing 300.5 in the modifier position and 213 in the counter position. So the first command here picks up this pseudo order pair and puts it into accumulator 3. So it sets the modifier and the counter in one go. The next order sets order 3 clears X3. This is the order that puts the modifier and counter into place. Now we start the loop, read the first block in from the main store, modifier 2, remember it will operate on block 300, and it'll read it into U4. Here we pick out we add in a number from block 4 in the computing store into accumulator 3. And exactly which number is picked out by the modifier part of X2. Now is the wonderful 66 order, you see, which adds 1 to the modifier, and it jumps if the resulting addition, if the addition does not change the block number. If the block number is the same, then you know that the information is in the computing store already. And in that case, you jump around here, and here's the count order, which reduces the count by 1 and jumps back if it's non-zero. So you spend most of your time just... that's been wrongly drawn. Yes, I sent a correction by email, which obviously didn't reach Simon in time. This
debugging programs on the fly.
0.2 plus is the second order in 0.2. I hasten to say that this instruction is correct in Simon's booklet. He didn't have the courage to draw the first pseudo-order pair, but then you could forgive him for that because it is rather involved. So anyway, the instruction that happens, this is the instruction that does all the work, and then you obey this one, and then this one. You go around like that 8 times, and then this one tells you the position number is 0, so the block number must have been changed, so you obey a new block transfer to bring it in, and then you go back there, provided the counter isn't 0 as well. And there you are, and it all happens. It's a wonderful system.
3 minutes.
Sorry?
3 minutes.
3 minutes, thank you. Right, well, a few other things to talk about. Hugh asked me to mention the programming courses we had. We started these very early on in, I think, 1955, before the prototype was actually working, but perhaps somebody can correct me on that. Certainly pretty early, and we had... Oh, thank you. Thank you, Jill. It was just about then, yes. We had a lovely, most elegant computing room, a lecture hall on the ground floor of 21 Portland Place. And we had room for about 20 pupils in there, and there's a photograph of it in Simon's booklet, where I'm explaining the square root routine to a number of members of the staff sending in for the visiting audience. These were very successful. We had, when the machine was available, the class would write programs and try them out. It was all very educational, hands-on and everything. The other thing I want to mention is the Pegasus autocode. Looks pretty crude nowadays, but here's a sample program which says n1 equals 1. N1 is the first of a number of counters, if you like, and that is an autocode command which sets its value equal to 1. This sets a variable number 101, to 0. This one carries the label 2, and it multiplies a variable in location specified by the counter. Counter contains 1, so you will square V2, V101, add it up. Anyway, you'll have to sort it out afterwards. I'm no good thinking on my feet. Then you augment the counter. You go back to the instruction labeled 2 if the counter is less than or equal to 100, and so on. And SQRT works out the square root. Very handy. Now, I don't have anything officially to talk about, but I've got a lot of documents here. Here is an interesting book, the Pegasus Programming Manual. I wrote this in 1958, mostly, while I was calculating pi. Bernard Swan was the most enlightened boss I've ever had. He was a most remarkable man. And he could clearly see that I wanted to write a book. So he gave me a year off to write a book. And I used to come into the office, you know, on a Friday evening, sit at the end of the computing room and write my book. And every now and again I would leap up, go across to the computer and change the tapes or whatever, and set it going again, and going back to writing my book, you see. And then I would do this until I got tired and I went home. I'd come in the next morning, bleary-eyed perhaps, and start the machine up myself, and it always seemed to work first time. I've never known a machine like it. Even my home PC occasionally doesn't quite work.
Not occasionally.
But Pegasus really was a most reliable machine, and I think this was due to all the sound engineering that you've have described to you, and the genius of all these people. Anyway, I wrote this book in 1958, but it had to be augmented by extra bits to account for Pegasus 2, magnetic tape, punch cards, and things like this. So the book, alas, was updated by other people who understood these things better than I did, and eventually appeared in 1962, really after that. But, you know, it was still used quite a bit. The library consisted of a large number of routines, subroutines, and so on. The idea was picked up from the Cambridge machine, where they had a library back in 1949, I think. Maurice, is that right? Yes. Well, I picked up their ideas and adapted them for Pegasus. And I learned a lot in the process. And here we have volume 1 of the specifications, including a lot of subroutines and things like the matrix interpretive scheme, which was very valuable. We had a similar routine working on Nicholas, and Peter Hunt, who was then working for the de Havilland Aircraft Company, was a customer of ours in Elliott's. He used Nicholas to do the flutter calculations on the original Comet 1, the world's first jet airliner, using 10 by 10 matrices. We could just fit 3 of those into the store. And I'm very glad to say that I was able to fly safely to Australia in one of those machines a few years later. This was before the tragedy happened, which was due to failure, fatigue failure, and nothing to do with the computing.
I'm very sad to have to bring it.
Yes, well, here we are. Come and look at this stuff
I'm sure we've been
afterwards.
for a long time.
And this is the programming manual we used to use on the courses. So come and have a look at them. But don't take them away.
No, I'm afraid we must move on. There will be some time at the end, I promise you. Next, we're going to hear about applications for Pegasus, and Donald Davis is going to tell us about his work when he was with Vickers Armstrong and using Pegasus for stressing analysis.
Stressing, is it?
Stressing, yeah. Welcome, Donald.
Thank you. If you want me to wear one of these things, I'll go. Will it hurt, Doctor? Absolutely. Oh. I think you're on. Thank you. Donald S. Davis. Why Donald S. Davis? Because there was, and I hope still is, a Donald Davis. NPL, I think?
He died.
He died. Right. He was a major player in our business, and I am merely a foot soldier from the Surrey foothills. I have been confused in name with the illustrious Donald Davis, which caused me considerable embarrassment. Now, Simon Lavington rang me up some while ago, and he didn't come directly to the point. He kind of introduced himself as Simon Lavington. I said, yes. He said, Professor Simon Lavington. I was impressed, Essex University, wow. And then he said, Pegasus. And when I heard Pegasus, I groaned inwardly, because this is the third time in quite a few years that people have rung me up and said, Pegasus. On all occasions, I've made the same response. I can't remember. It was 40-odd years ago, and a lot of it has gone from my mind. Simon's a very nice chap, and very convincing, and so on. So he said, come along and tell us a few funny stories. So maybe I'm going to come along and tell you a few funny stories. I was at Vickers Armstrong at Weybridge, and it's necessary to tell you a slight bit of history. sought a job there in 1953, in the autumn of 1953, into the stress office, which is down here. Why, if I told you, you wouldn't stop laughing. Why I've sought that job seems now ridiculous, and why the chief stressman took me on sounds equally ridiculous. But there I was in the stress office, attempting to become a trainee stressman, attempting to become an engineer when my background was purely mathematics and physics. I failed miserably, as it says in my bio. And while I was kind of swanning around there, wondering what I could do, whether I could move to something else, I found a Brunsviga. Brunsviga? Yes. And I found that I was quite good with this, possibly due to the fact that I'm half left and half right-handed. So I was quite pleased with that. Then I found a Mercedes, not the motor car, but an electric machine of incredible noise, which I couldn't use very long because I was told to leave the country. And then moved on to the Pegasus, or the desk shaker, and eventually onto the Munro and Munro-matics, which were very smooth, sophisticated calculating machines, electrically driven, automatic. During this period, I was helping out colleagues or anyone else who'd like to come along and have a few sums done. Now, what drew the attention of the flutter section head was that one of his men was now getting all his sums right, and he was getting them right quite quickly. So he wanted to know why, and he found me. And he said, "You're wasting your time in the stress office coming to the flutter section." Now, George already mentioned flutter. I'm sure you know what flutter is. Flutter is sustained or vibration, which usually causes things to break. And in the aircraft industry, when you get flutter, it occurs in about 1/10 of a second. And when that happens, your elevator comes off, your aircraft becomes unmanageable, and you crash into the crowd in an air display. And so it's not nice. But the more mundane one is, of course, the bridge of light, which is an absolute disgrace as it vibrates. So there we are in the flutter section. And I hadn't been there very long before I began to discover some things. One was that matrices dominate the field in the flutter section. And there are more ways of skinning a cat than you can imagine. I'd learnt about matrices, they're a bit obscure, commutative, non-commutative, something like that. And if you want to invert them, you get the matrix of the minors divided by the determinant. No, that's not the way to do it at all. There are numerical ways, and these ways were explained to me, and I applied myself to them. At the same time, I was looking into a little report called Downwash due to oscillating doublet strips, probably well known to you all, which I didn't understand, still don't, but it produced a matrix. And that matrix had to be inverted, and it was somewhere around 10 by 10. And so I sent it off, and I sent it off to a computer, and that computer was at Lyons. McDonald House people. We went there, and saw big toadstools and a pervading smell of pork pies. So they inverted that matrix for me and sent it back, and we did a few sums, and we got pressure distribution on an aircraft wing, which is totally and utterly ridiculous. Instead of kind of saying that's wrong, the head of department said, "We'll go and see the experts." So we trotted off down to the RAE, and we saw the experts, and they said, as experts do, "Very interesting." What they should have said was rubbish, because rubbish it was. Why was it rubbish? Because in writing them down, and we used to do it by hand in those days, I had written matrix A suffix ij equals, and then this 10 by 10, and then I'd written underneath, and please invert matrix A suffix ji, a slip of the pen. They'd done just that, they transposed it, and inverted it. What I got was the inverse of the transpose. When I transposed it back and did the multiplications, got the right answers. But here was the lesson. Getting it right is not just getting the right program. At this time, we also have more problems. When you invert a matrix by hand, you using a calculating machine, you put in row and column sums as a check. On the right-hand side of the matrix, you put in the row sum, bottom of the column with the column sum, and then you add the column sums together, and you add the row sums together, and they become the same. You put that in the bottom right-hand corner, and this is used as a check all the way through. No, they sent off an 11 by 11 matrix to Pilot Ace. And Pilot Ace, they sent a message back and said, we had trouble inverting this, 12 by 12. And so you would. It's identically singular. But they did it. Good for them. Right. Finally, the CAM problem. Why am I emphasising this? I'm trying to make a point. The CAM problem. Vickers, Armstrong, shipbuilding, knowing that we were computer experts, and that we knew how to use them, we had a distance, sent us a problem. And this was to define thousands of various positions on a CAM so that they could get them out by spot drilling them, and then they put the CAM down in the depths of a warship, and when you rotated the CAM, the guns up on deck followed, and they went bang, and it hit the enemy, just like that. And it was a fairly sophisticated trigonometrical formula, and we sent it off to, you got it, Lions. And it was to take it at step intervals, very, very small fractions of a degree each time. Oh, back came the answers, hundreds and hundreds of them. And a moment of madness, we had them bound up in a book with a leather cover and tooled into it in gold. On the front was the CAM problem, and I personally took it down to the Vickers place, and the man looked at it and blew his top, because only when the angle was 0 were the numbers right. All the rest of the time they were wrong. Why were they all wrong? Because Lions had done it in fractions of radians, when we were working in fractions of degrees. Again, there's a lesson. Now, that was history. So we get to Pegasus at last. The plotter section was becoming more and more important. Now remember, this was a company in which if you walked into any of these offices here, you would find people doing this, some using slide rules. Slide rules, okay. Most of them were straight, some of them were round. The first thing I had to do when I got there was buy one. Fortunately, a man had some in his drawer just there for sale at 2 and 6 each. So I acquired one, and I used it for many years for drawing straight lines. But they built the Valiant bomber, which at one time was the dominant bomber aircraft in the world. And they built the Viscount, the successful airplane, with slide rules. The Times were catching up with it. And catching up, particularly in the flutter section. So the head of the flutter section, a dynamic man, he got in cahoots with another group at our site, which we call GW. In other words, they were the guided weapons. What were the guided weapons doing? I don't know, it was secret. And they got together and they made a case for a computer, and that computer was the Pegasus computer, and it was agreed. And so a Pegasus computer was on the point of order. In fact, we started going on programming courses. Who's we?
Did you have a manual?
No. I don't think so. It wasn't written yet. We were the mathematical services. Where do we come from? Well, the head of the flutter section was put out a note, anybody who wants to come and join this new computer department. I went home and said to Madam, we're going to do this. She said, join it. I think computers are the coming thing. So I joined it. And there we were, mathematical services. Why mathematical services? Because they called them mathematical services at the NPL, and we had a lot of respect at the NPL, despite that fact that the Department of Ace, which we won't go into. So along came, we went off to programming courses, and then Vickers, Armstrong's aircraft decided to join up with English Electric Aviation. And what did English Electric have? They had deuce. And they wanted to know why we weren't getting a deuce. Why didn't we want a deuce? Well, to start with, there was some terrible tales about Juice. There was Gert and Daisy down at the RAE, which started on the same problem together. They'd finished at different times. There was optimum coding, which was frightening. There was a story that the head moving up and down on the drum, because they had a moving head, caught fire, which is not too clever. And worse than anything else, they were punch cards. Now, understand, but I'm not going to talk about the age-old debate between punch cards and paper tape. Just sufficient to say that a paper tape editing device is little like that. And if you can flip it open, you can cut it, join it, thing, and it goes in the pocket. And it can drop out when you take out a handkerchief. You know, it's a kind of feature, isn't it? See, what's that? Oh, just computers, you know. Can you carry around a hand-editing card punch? Well, we got past that, and we were preparing now for the delivery of the Pegasus computer. So we called in the works engineers. We're a big company, remember? Works engineers, they were delighted. They'd like anything with budget attached to it. And they came in, and the floor was concrete, the walls were around us solid, and the internal partitions were metal and glass. And so they said, you're going to run cables? Great, we'll dig up the floor. So they dug it up with pneumatic drills. I've only heard recently from George Belton that you had false flooring on the first Pegasus. We didn't have false flooring for many years, so they dug up the floor, and they were ready. And down came the Pegasus. Meanwhile, we were still going up to put in place. And I had found the matrix scheme. And of course, I was up to my eyeballs in matrices. The matrix scheme was marvellous. I was writing programs. Oh, no problem at all. I remember putting it on the machine, starting it up, running the tape, turned round, and there was Chris Strachey. He said, anything interesting? I said, oh, just matrix scheme. He was underwhelmed. Next moment, he was interested because every light on the machine came on. All the track lights, bang, full. Writing with overflow, hooting like mad. Matrix scheme. I'd managed to divide by 0, I think. But the matrix scheme was there, and it was growing more and more important. In fact, it was once said that we bought the matrix scheme, and Ferranti gave us the Pegasus with it. No, I don't think this is a... This is a transparency. Oh, it's on top, is it? Oh, yes. Thank you, sir. Right. Well, there's our first Pegasus. You see the walls and the things, all this kind of jazz. And that is Miss Joy Baird, a delightful young lady, Scottish, with sinews of steel and a mind made out of brass, who kept us on and off the machine. I mean, she looks quite docile there, but she didn't half frighten the rest of us. But we had an organisation. The organisation was what we call close-shot programming. In other words, our little gang used to write programs. We used to punch up the tapes on teletypes, or post office things, I seem to remember. And very good care was taken to make sure they were right. We had comparator units. Compare two tapes, punched at different times, or put one in and punched the other and compare it. Yes, we did everything to make sure the data was correct. Yes, and that's where you got your problems with your customers. And this is where the big problems of computing come. Because Pegasus, basically, is a reliable machine. It was so reliable, it was a damn nuisance. You see, we'd known it was reliable because when we first went up to Portland Place, they showed us the engineer. He was reading the paper. And he was completely at his ease. And they said, he is at his ease because the machine is reliable. What's more, he can do the Times crossword in 20 minutes, which is quicker than Inspector Morse. Yes, it was reliable. But it was so reliable, our engineers got cocky. What's wrong with the machine? Wrong. You must be joking. Can't be anything wrong with the machine. We ran the test this morning. We reduced the voltage. We ran up and down our screwdrivers, you know, along the packages like that. They're perfect. Well, you did get problems with it. I'm in the hole in the drum. I had a hole in the drum, yeah. It took 43 minutes of running a rungo cutter integration routine to get to the hole in the drum. The machine stopped, parity failure. I said, there's something wrong with the machine. No, says Ron, there can't be nothing wrong with my machine. I said, well, he said, run it again. It won't happen. So I ran it again, in 43 minutes, it stopped in the same place. He said, that's funny. He said, just a minute, I'll get Dave in. I had to run it again. These weren't done all the same day, I can tell you, because... And after 43 minutes, it failed again. So they got the drum out. They said they looked on it with a microscope and they found a hole in the drum. I don't know. He said, your digit has fallen down the hole. There was, in fact, a design or manufacturing fault on Pegasus. It was due to our magnetic tape unit. If, in fact, you gave a rewind order on the second part of the order pair, it didn't rewind the tape. But that didn't matter because it's usually at the end of the job and you press the button anyhow. But there was a design error. How far have we got? We've got our computer in, we're working away, and now we've got all the problems with the customers. Customers, because we're a closed shop, we write the programs, we run them. Even with a matrix scheme. Matrix scheme, so simple. No, that's not a simple one. This is simple. You know, reading the 10 by 12. Reading the 12 by 16, multiply the 10 by 12 with 12 by 16, output the answer, and there you are. Funny, isn't it? You're reading in the 10 by 12, you've got a checksum at the end of each column. In the first column, it stops. Checksum is wrong. You go back and say, hey, your checksum's wrong. He says the machine's wrong. Don't argue. He checks it up, he's got the wrong number, or he's added them up incorrectly. And it took an age before a simple job like that could be done the first time. Get data correct was an extremely difficult job. But they came round in the end, as did these other people. These other people, they used to run Pegasus. I'm giving this, I'm giving me this, a nice list. Jolly good. Now the one that's interesting to me is that one. Because they put a link into the Pegasus exchange scheme. There was a software scheme. These were days when we were naive. We used to put valuable programs into an exchange scheme and you could write in and they send it to you. We didn't have much, we just had this thing. And I'm afraid Simon's not at fault here, it's me. If you have given S points to fit an nth order polynomial by the method of least squares, this is a well-known thing. You can express it in matrix terms and you can get the coefficient polynomial out and you know it works like a charm. Now I've written a program for this, and used preset parameters, and you know, it was almost the kind of thing you knock off just before coffee. It was so simple. And it worked. Not that we ever used it, but there you are. But we didn't have anything to put in the exchange scheme, so we put that in. And damn me, we had inquiries from all over the world for something so simple. But the Hawker City boys had something much better. They had the Maltop-Richardson system. What's that, you say? The Maltop-Richardson, never heard of it. It is, in fact, a way of dealing with aerodynamic theory. Because what was happening at this time, and I've lost the little slide, is that theories which previously were known of but couldn't be implemented because they were too computer demanding or too demanding of computing day, now became available. Oh, there it is. And what was happening was, at Weybridge, was that with that program, those, the aerodynamics, were sucked into our system. And over the years, one by one, they crossed that event horizon and found themselves in the black hole of Pegasus, which they couldn't get away from. And the only people that never got sucked in were the project office, who was supposed to be, right at the cutting edge. But all the rest did. Drawing office, aerodynamics, wind tunnel, making wind tunnel models. The Molot. You draw out the airplane full size on flat sheets of metal, and men with kneecaps and felt shoes climb all over it. And if you want to know anything, you go up and ask people in the Molot to look at the sheet and measure it out. Well, we got rid of that. Eventually, it took time. Weights, they came in quite early because they wanted to keep tabs on the weight. They used to say, try to keep the weight of the airplane down, but they could never keep up. They never knew what the whole latest guess of the whole all-up weight of the airplane should be. By the time they found out, it was too late. How much more time have they got? None, right. And here you see us in all our glory. 3 Pegasus. Pegasus 1, Pegasus 2, and the original from the Francis Centre. The original Pegasus 1. We got the little hooks up there. We were considering putting in a Mercury, which you can buy second-hand from Shell. Shell people got us more or less drunk and then took us to St Mary's Axe to look at it. And we were very impressed until we saw the air conditioning plant, which was like the inside of a battleship. So we got turned off that. We got the last Pegasus down, and then eventually history caught up with us. We went on to a 1905, which we would not buy until they got a matrix scheme on it. That's the fact, they had the right one. Now, I got this run back to front of that mattress. Some people, I think Simon said to me, what? He said, are those? Those are dust gatherers or sound baffles, whichever way you look at it. Because we have, as I said, metal walls, glass windows, 3 Pegasus machines, they all made a noise, and guess what that is over there? That is subsidiary air conditioning, because the works engineers haven't put that in the first instance, had they? This is quite an interesting device here, because that is reading a tape which comes from flight test. In other words, testing the aeroplane, automatically recording the data, bring it over and analyze it. Half-inch tape? Yes. And how many people in the department had a splitter which was split it into quarter-inch tape? Everybody but me, and I didn't have a tape recorder. Minus time?
Yeah.
What can I say?
Minus time, don't worry.
I will finish off then. Eventually, we were going to move to 1905, and so we ceased our closed shop programming. We got hold of the engineers, and we taught them the language of then the future, which was Fortran. And they got on with their own programming. Meanwhile, back in the ranch, we were developing new systems. Some of them quite extraordinary, but they started on Pegasus, and they went on into the bigger machines, eventually the 1906A, and then on to IBM.
Thank you very much, Donald. That was most stimulating and illuminating. We need to move on. We're 10 minutes behind the tight schedule that I've been given. Our next speaker is Judith Millage, who's going to tell us, do we need a comfort break? I think we need to move on, Judith. Judith, going to tell us about the application of Pegasus. No, let's move on. Let's move on. Judith is a physicist. And has worked in South Africa and done crystal structure analysis at MIT before returning to UCL in 1953 as an ICI fellow.
Thank you. Well, I'm sorry that we're a bit behind time, and I will try to be as quick as possible.
I note that I'm down as formally with University College London, which I hope means retired, because actually I go there every day. But so anyway, it's Pegasus at UCL that we're going to talk about now. Now, in 1945, Professor Christopher Ingold, who had known her in Leeds, invited Kathleen Lonsdale, who that year became the first woman to be elected a Fellow of the Royal Society, to come from the Royal Institution and establish a crystallography unit in the chemistry department at University College. Here she is, in fact, with a couple of suitable statements from the press when she was elected the first Fellow of the Royal Society. And so the whole of this depends on the fact that she had this unit. Now, in most chemistry departments, people solve structures for their colleagues, but she was a physicist in the motion of atoms and crystals, which she saw as the pathways of chemical change, and her group was mainly concerned with studies, as a function of temperature, of crystals containing small organic molecules, such as urea and anthracene. Now, I have to tell you a little bit about crystallography, in fact, in case you don't know anything about it. Now, crystal structure analysis, I need some slides. Have we got a thing here that...
What?
Slide? No, just got slides up top. Under there. Isn't there? Fine. That's the next one, isn't it? Yep. Now, essentially, crystal structure analysis involves two stages. First of all, you have to collect X-ray diffraction data, and you can either do it on a photographic film like this, in which case you've got to identify the spots and measure how strong they are, or you can use a diffractometer, which in fact means that you have to collect the spots one at a time, and both the crystal and the counter have to be moved in order to get each spot. Now, both of these activities are simple mathematically, but they involve quite a lot of calculation and they're extremely tedious. Now, crystal structure can be solved by one of two techniques. One involves Fourier methods, where structure amplitudes, which are related to diffraction maxima, can be combined in three-dimensional Fourier series to provide a map of the structure. Now, here, in fact, is such a map to a structure of urea, simply made by combining these various terms. And in fact, this is one done photographically by a machine called the von Eller photosommeter, which is also here in the Science Museum. Now, the process is again mathematically very simple, but it's extremely tedious because the phases of Fourier terms can't usually be found experimentally. And the preparation, therefore, of this sort of map has to be repeated many times. And in the days when we're talking about, the figure fields had to be produced by hand. And so that if you wanted to make a map like this, you had to compute, you then had to draw on the figure field your electron density peaks. So that in fact, this was a very tedious matter. Now, the other technique for solving crystal structures involves using least squares. And in fact, this means that you propose a trial structure for the crystal and you then improve the agreement by least squares analysis. This is essentially a matrix operation and it's again tedious to carry out manually. So this means that crystallographers were among the first people to realize that electronic computers would be of enormous benefit to them. And all early machines were immediately besieged by the nearest crystallographers. Now, just across the road from Kathleen's laboratory at University College was the engineering firm of Babcock and Wilcox, who were to acquire a Pegasus computer in 1958. And in fact, they said they would offer free time on it to UCL. Now, of course, what they hoped was that the engineering departments would take up the offer. But in fact, I was one of 3 crystallographers who immediately enrolled in the programming course offered by Ferranti in their Portland Place offices late in 1956 in order to learn how to write crystallographic programs. Now, our laboratory used photographic methods, the first thing we looked at, because thermal motion often involves diffuse scattering, which is difficult to measure with diffractometers. And least squares methods were used because it isn't necessary to produce Fourier maps like this during the process. So from that time onwards, I spent most of my time over several years in writing two programs. One for intensity processing, for getting the data off the films, and the other for using least squares to solve structures. Now, I had, how do I get the slide off? Oh, sorry. Let me get that. Oh, well, fine. So I had an enormous amount of help from one of the programmers in Portland Place, Derek Millage. We were married in 1958, and as this abstract shows what could be done in 1960. Now, this is really quite remarkable when you think of it. You've heard about how you have to program Pegasus. Intensity processing we could do. A comprehensive structure factor and diagonal least squares program for refining structures, special facilities for use at the trial structure stage, generating coordinates, rotating molecules, molecular geometry program. All of this was done within about a year or so of this kind of programming, and that was what we basically did. Now then, we improved this further to some extent, and in fact, I actually wrote a paper here, and you'll notice that this is a question of high-speed computing. Think of it, the speed at which you could actually do this work. But in fact, it was increasingly possible to use this sort of program to actually solve structures. Now, one of the other things that Kathleen Lonsdale had been particularly interested in was diamagnetic anisotropy of crystals containing organic molecules. Her electromagnet from the Royal Institution is also in the Science Museum, and the structure factor least squares program was altered in order to make use of data of this kind. And in fact, it was really much simpler than it looked. If you had a small molecule and you knew how large it was, you knew where it would sit in the crystal, and all you had to do was to rotate it using the program, compare it with the observed values of diamagnetic anisotropy, and you could solve your structure even on Pegasus in 5 minutes. Now that was something, of course you couldn't do it with a big molecule, but then we weren't interested in big molecules. And ever. So then sometimes it wasn't quite as simple as that. This was a structure of diphenyl sulfoxide in which the things suggested by the diamagnetic susceptibility measurements was a bit wrong. That's the dotted one, and in fact the right answer is the one with the solid lines. But in fact it was very quick to alter this, and a rotation of about, 30 degrees meant that the thing refined immediately. So actually, for the sort of things that we did, this was a very powerful machine. It meant that we could do very well. And we continued to use the Babcock Pegasus in as much time as we could afford on the Pegasus at Northampton Polytechnic. And when the Pegasus machine was going to be moved out of Portland Place, we wanted to buy it. Now, by this time, the UGC was funding Atlas, and there were problems about funding other machines in London University. But when the Scandia machine, in fact the one that is now here, was offered to Kathleen Lonsdale as a gift, the SRC funded the installation in January 1964 and provided spares and 1 hour per day preventive maintenance for 5 years. Perhaps the greatest virtue of the design as far as we were concerned, package construction and engineers' tests to identify packages likely to fail, meant that the downtime was negligible and wrong answers due to machine errors were virtually eliminated by parity checks. So having a machine on site was a great benefit to the group. I think I can get the slide on again. Right. This, in fact, is the group of people who were working on this One of them, Mike Glazer, is actually here this afternoon, I'm glad to say. But you can see that there's a certain sameness about these molecules. We weren't doing a lot of different things, we were doing variants on a theme. But there was a lot of work to be done. Now, sorry, I've lost my place. We had to, the point that I wanted to make here is that we did a lot of work on short-range order and order disorder in solid solutions. And this means that you had to do a very large number of data sets on one given system, which means, in fact, that you were really doing as much work as people who were using much larger crystals. And so that was I think I've got the next slide. Let's try this. And so we did manage, though, with Pegasus to make some use of a pseudo-graphical output. And you see here that we're just using the minuses and the erasers to show statistical simulation of short-range order. So this, of course, was before the days when there was anything that you could actually do on Pegasus, desktop publishing and things like that. Graphics didn't exist in those days. And so that's one of the reasons why I'm showing you, or would be if I could find my place, on the, apologise for this, yes, we looked at the short range order, yes, sorry about that, and the next slide, if I can get it to come up. Yes, this is an example of the sort of work that Kathleen Lonsdale was interested in. You see, it's one single crystal turning into another. That if you look at the top picture over there, you'll see that there's lines of spots. And if you look at the bottom picture, you'll see that the original set has got much weaker, but another set has arrived. And that, in fact, was the sort of work that we did a lot of in the group. Sorry, I apparently lost my... So the thing that we did after that was when Babcock's got rid of their computer, they actually offered us their air conditioning plant. And that, in fact, was an extremely useful thing. They also offered us some money in which to install it on our machine. Well, we were even more fortunate because a member of Babcock's staff, Dave Wally, who had joined the statistics department at UCL and who, together with his wife Maureen, not only helped us with new programs, but was also able and willing to help us to keep the machine going. And we funded some of the maintenance ourselves, including revalving the machine shortly before we stopped using it on a regular basis. Now, from 1968, that is when SRC stopped supporting us, we had to fend for ourselves financially. And I scrounged as many spares as possible from any Pegasus that was being scrapped. I bought one Pegasus from the Ministry of Defence for £5. And we also obtained a graph plotter, which was connected to Pegasus via a package made for us by Peter Fuller. Now, the graph plotter deserves further mention. It had two main uses. One was to simulate X-ray diffraction patterns. And here you see is a picture of a Weissenberg picture. It's actually ATP, which we did for Oliver Kennard, who was trying to solve the structure at that time. And this was extremely useful. If you have a very large unit cell, it's a great chore to identify this sort of thing. And the other thing that we did with the graph plotter was that we looked at the morphology of crystals. Now, that is... Slide on. It doesn't go on. And the morphology of crystals, this was quite a tiresome exercise because we had to... will the slide go on? Oh, very good. Yes. Fine. That's the my paper appears to have got lost. Yes. This we first of all we looked at the indexing of photographs, and then this question of doing morphologies of crystals that's a very tiresome thing to draw. I mean, there are rules for doing this, but it's tiresome to draw. And in fact, this particular set of experiments, of pictures, was accomplished by a very tortuous operation in which the necessary parameters were computed on the IBM 360. A routine included to reverse the most and least significant bits. It was then transferred to a machine in the electrical engineering department where they punched out on 8-hole tape, which was then turned over and read using the Pegasus 5-hole tape reader to control the graph logic. So but then you see in those days, what was there? There was nothing else. So anyway, pressure on space, more computing power available within UCL, and a change in the direction of our research made Pegasus less and less necessary. And we were considering which museum to give it to, with the proviso that it should be kept operational, when a group from ICL, who were now associated with Fujitsu, visited Japan, where a valve machine was kept in operation. Now, on their return, they were looking for a machine to keep operational themselves. And so after a farewell reunion of many of the original Ferranti staff at UCL, Pegasus, with all its spares, was eased out of our fire doors and returned to West Gorton, whence it came. Yes.
Thank you very much for that insight. Our last speaker
is Chris Burton. Chris has taken on the task of commissioning the machine we're going to see upstairs later on. And he's going to tell us the story. Chris?
Thank you very much indeed. Let's see. Now, when I prepared this slide, I was astonished to see that that machine number 25 is 42 years old, which coincides with the number of bits in a Pegasus delay line.
I know.
So I think Douglas Latham was right all along. You'll notice that the Pegasus, its middle years, 20 years, were very productive. It had 5 years at West Gorton, shipped to Sweden in that time and shipped back again. And again, I was astonished to see that for 17, 18 years, it's been in the hands of the Science Museum. And I can lay claim to have had hands-on this machine throughout that time. And I thought, great, I've had the longest experience working with this machine. But of course, I realised Judith has had 20 years. But I'm the second longest lived person using this machine. Now then, I'm going to focus on that last section, the time that it's been in the hands of the Science Museum. In 1983, as Judith said, the machine the room was needed at University College, and the machine was at risk of going abroad. And by great good fortune, the director at ICL West Gorton, David Dace, noticed this and said, no way is that precious UK artifact going to go out of this country. We will provide space in the place of its birth at West Gorton for us to put it on display. And he funded the room and the movement of the machine there so that it could be used for demonstrations, and we'll look at that later. And there the machine remained for 4 years. Why didn't it go to the Science Museum at the beginning of that time? Well, the Science Museum didn't have storage space, let alone gallery space at that time. So in a way, it was known that it was a holding operation at West Gorton, and eventually the Science Museum would acquire it. At the end of 1987, new management at West Gorton demanded the space. You'll see the whole of this story is this poor machine occupies space which other people want. And
the room that it took up at West Gorton was required, so the machine had to go. Fortunately now there was storage space at Hayes in Middlesex, and the poor old machine was wrapped up and put into store for a couple of years there, until 1989, when the start of the Computer Conservation Society and the curator of computing's ambition to get this precious artifact working somewhere, if not on display. And we got that machine working in the old canteen behind here in what used to be the car park behind the museum, and there it was for 7 years, many happy years of keeping that machine going. And lo and behold, unfortunately, we needed the space. The old canteen had to be demolished for the new welcome wing, and so it was on the road again, this time to the Blythe Road store in West Kensington, and there we again knew that it was on hold because there was a gleam at the end of the tunnel that this machine would eventually be put on display, and so there we kept it going for another 4 years, and here we are today. So, starting way back there in 1984, here there was a farewell party at University College for the machine. There's Les Mander there, Les Manders, who did the maintenance in the later years and got the machine working for us, or advised us on the machine working when we moved it to ICL. And remember, it went to ICL because David Dace had the foresight to provide the space. Here it is being dragged out of the semi-basement at UCL and arriving at West Gorton. There's the tower block at ICL West Gorton, and we're in the car park behind the R&D building unloading the power supply, and there it's arrived in this specially built room which was carefully contrived to have a sort of cold shade of light blue and 1950s fluorescent lights, and we even had an older black telephone to give the feeling of a 1950s, 1960s system. There's the main computer in the new room, and you can see over here on the right-hand side the part of the power control unit. This was serious engineering, heavy power. The 1200 valves required heater supplies and high voltages. It used 15 to 18 kilowatts of three-phase power, no plugging it into the three-pin plug. There was a motor alternator system which weighed about 3/4 of a tonne for stabilising the power. Here's a picture of part of it, and Martin is pointing over to the left to the other alternator at the end of that setup. Real serious stuff. The heat provided by all this 18 kilowatts had to be got rid of. And in this particular machine, there's a refrigeration system with plumbing to take the heat out of the system to the outside of the building. And for example, between the power supply unit and the central processor, there are 50 heavy cables which have to be installed or disconnected as you move the machine. Here is the power supply unit which provides the high voltages. Really a cartoonist's dream in terms of the meters and the controls and the fuses and the big valves. I mean, here the great big 12V1s which are about 7 inches tall and so on. Anyway, by the beginning of 1984, we had got the machine working with the help of Les Manders. Who are we? Well, a colleague of mine, Keith Wood, and I were the primary people working on the machine. We were invited by our management, we both worked for ICL, we were invited by our management to see if we could help with getting the machine working again. And here on the 23rd of March, ICL once again had a party to welcome Pegasus home, the place of its birth. I can't think of the number of occasions when glasses of wine have been on these consoles. The machine's moved so many times. And so there was the party to welcome the machine home, and for example, it was used for publicity. The old and new, of course, refer not only to the machines but to the operators. This was publicising an early ICL personal computer. I think it was an 8 megahertz 8086 with twin full height 5¼ floppy drives. And we could use this for benchmark comparisons between old and new, for example. For example, time to count the number of primes in a range using Pegasus autocode, a high-level language. It takes about 7 minutes on Pegasus. If you program it in machine code, about 38 seconds. On a personal computer of the time, and I think this probably refers to something like a 386 or 486. Use a high-level language basic. It's not measurable. It's under a second, and if you do it in machine code, well, it's done it in no time. So this was good for the press. We could show how technology had moved forward. What happened in those 4 years at West Gorton, mainly Keith Wood and I did the maintenance, spare time. We would work in the evenings. I've been looking through the logbook, and the number of evenings and Sundays I was in at work doing this, I can't believe. The machine was switched on in that 4 years on 50 occasions for a total of 110 hours. It doesn't seem much, of course, in 4 years, but on the other hand, it did its job, demonstrations to VIP visitors, including His Royal Highness Prince Michael of Kent. And that was quite an enjoyable time. Now, at the end of 1987, I found this mysterious entry in the logbook in my writing. Attempting to switch on for check, a visit of a Mr. Swade from the Science Museum. Now, I'd never met Doran at that time, and he had come up to see the machine because it was known that the space was wanted at West Gorton, and he was going to find storage space at Hayes to store this machine. For 2 years it was in store and in limbo, and as it were, we forgot about it. However, in 1989 the Computer Conservation Society was formed, and one of the first things was to form the Pegasus Working Party, and John Cooper was appointed chairman of that working party. John Cooper had been at Northampton Poly, later City University, and an early activity of the members of the working party was to be indoctrinated in the mysteries of curacy, curatorial practices in a museum. We were told in no uncertain terms that the objective in keeping the machine going was not to try and get the wages out by Friday. The objective was to preserve the historical integrity of this machine. Now, for many of we volunteers in the society, who were engineers and programmers, we'd had a different culture. Now we had to learn the museum culture. And very interesting all that was. And even now, today, it's sort of ingrained in me. If I see an old food, an old thing, don't do anything to change its historical integrity. It took us 12 months, essentially, of very careful work, to get the machine out of store, reassemble it in the old canteen, and get it recommissioned. We were very tentative about how we did the work in those days. Bear in mind, we were volunteers. We would come in perhaps once a month for a day. So there wasn't a lot of hours that we devoted to this. We couldn't. Tony Sale was here full time and sort of facilitated everything. But as far as the working party was concerned, there was not many hours, and we were very careful not to do any damage to the machine. Sadly, John died in full flight of this in 1993, and his legacy is that I think in all the active working parties, this fantastic synergy between we, the volunteers, with the technical expertise and understanding of this kind of equipment, and the museum, who've got the national responsibility of making sure these artifacts are properly preserved and displayed and so on. And this is something that over the time since 1989, the computer conservation's existence is something which has been developed in these working parties, and I think is something that we can be very proud of in the country, not only in our society. Now here it is in the old canteen, nice big spacious room. There were other objects in there, the 8803 behind there, and the deck stuff over on the right, and quite a nice spacious place to work. And we would have open days and in steam days, and I can well remember how hoarse we were explaining to the people how this machine worked, faced with the din of the air conditioning and the refrigeration and the motor alternator set, shouting over this noise enthusiastically, explaining to people how the machine worked and so on. Mostly the people we're talking about are enthusiasts such as yourselves, who knew what computers were and were fascinated to see this old thing from the past resurrected. I took over the acting chairmanship in 1993 until 1997, when Len Hewitt became the chairman. At that time I had other preoccupations with this baby machine in Manchester. And in 1994 the machine was put under wraps again because the space in the old canteen was required for offices. Over our dead bodies, said we, we're not moving that machine. Okay, said Doran, we'll cover the machine up and we'll build a little room around it so that we can, as it were, cocoon it and operate it in this little room. And here's the little room. It's in the same place, but the room's been built around it. Very nice, clean little room where we could still keep the machine going, keep it maintained, improve the reliability and demonstrate it to the public. That was about 1995. Horrors, 1 year later, you've got to move. The imminent demolition of the old canteen to make way for the new welcome wing. We'd have to dismantle and move this great big machine once again. The 7th time it's in existence, it's been dismantled and moved. We very firmly said, we can't guarantee that we will be able to keep it working. Tony Sale voiced this on behalf of the working party. Every time we moved it, something stretched or moved or twisted, a fuse blew, some wires touched. We had no way of guaranteeing that we could keep the thing working. But still, better to move it and take the chance than scrap it. So we dismantled it once again. This time we video recorded our dismantling procedure so that people in the future will be able to see what it was we did wrong if it didn't work. However, we were moving now out of the South Kensington to the Science Museum's overflow store in Blythe Road, West Kensington. And we were provided with some space on the ground floor there. Quite a nice amount of square footage. And it was in amongst all the welcome collection of early medical equipment. You can see a Louis Townes dentist chair up at the top. Okay? So it was a bit of an eerie place to go if you were sort of working silently, going off somewhere and you passed all these mysterious torture chamber equipment in there. We had the nice corner there, and it was such a huge barn-like building, we took the chance on not using the air conditioning. We thought that it would be sensible to not waste time installing all this plumbing because we knew this was a holding operation. So we left the top off the machine, let the hot air blow through and fill up the room there, and the machine worked well. There you can see part of the working party, Doug Brewster, Derek Millage, Martin with his back to us, and Peter. And we would go across there perhaps once a month, once every 2 weeks, depends what the urgency was, keep the machine going, improve its reliability, check out programs. All on a very much a temporary basis. And there's another shot of it with then Hewitt, the chairman of the working party there, and again Derek and Martin. And you can see it's all a bit ramshackle and ad hoc because all we want to do is just keep it going, keep it reliable, because the light at the end of the tunnel was it's going to go on the gallery sometime. And that happened last year. At the end of last year, well, we actually made the move. I should just say that at Blythe Road, it was a very temporary layout, slashed together. We feared that the machine would become unreliable under these conditions. It was, however, as reliable as ever. Indeed, its reliability considerably improved. By that I mean that we could run the test programs, for example, for an hour or two without any problems. We could switch on, as people have mentioned already this afternoon, you could switch on and lo and behold programs would work without any intervention. Bear in mind that in the kind of regime that we're operating, where we're switching on the machine for a few hours every couple of weeks or so, there doesn't seem a lot of point in doing the traditional Pegasus preventive maintenance, where you take out packages and offline test them. We work on the basis of if it ain't broke, we don't fix it. Because movement of anything like unplugging, plugging a package is risky on a machine that's over 40 years old. So we just mend it when it's broken. And this was the period, 97 to 2000, when Derek Millage really was helping us to understand the nature of the faults that did occur when we were on margins, when we were running test programs, to pin down all the detailed things which were broken where we, the rest of the working party, as engineers, hadn't got the understanding of the software, and really it was a tremendous credit to him that he was able to put all that over to us. But I mean, apart from Derek, the rest of the working party, all the way through, since 1989 today, have doggedly come along and looked after this machine. And when you think the number of years, it's just sort of, it's been pushed from pillar to post, it's a great tribute to all the members of the working party. And finally, we made our 8th, and is this our final move, to the computer gallery at the beginning of this year. And there is a picture of it on the way into the gallery. You can see a wooden builder's hoarding behind the power supply there. That hoarding came down yesterday, and so it's only today that I've seen the thing in all its glory. And in the computing gallery, you can see some of the air conditioning at the end of the power supply, a great big turbo blower there that circulates the air, and so on. So there we are, 17 years of pillar to post, and we've kept the thing going throughout that time, and it's slightly flaky today, but not...
It's a great tribute to you and the people who helped you.
I'm only a hanger-on. Those who haven't seen will see tonight the prime numbers by Silvio Eratosthenes, calculation of unit cell parameters and the music program. It's easier for me to explain that when the thing is being demonstrated, and you know all about that. Thank you very much.
Thank you very much. Thank you very much. Well, I promised you some time for the discussion. We have, unfortunately, only 15 minutes. Because those of you who are not coming to the reception need to leave here no later than 10 to 6 because the front doors will be locked. Before we move on to the discussion, Peter Hall wanted to say something.
I'd just like to make an apology on behalf of Sebastian Ferranti. He was due to come. He was very much looking forward to coming. But unfortunately his wife is very, very ill, very seriously ill. She was sent home from hospital a couple of days ago and is remaining by her side. I talked to him yesterday. He mentioned quite a few of the people here how much he would like to have met them again, how proud he is of his association with Pegasus, and he would love to have been associated with today. I'd like to say that we all owe an awful lot to him and his father. I know we've got a lot of support from NRDC and people like that, but without their personal money, none of us would be here talking about Pegasus. But they put a lot of money into it. And they're going to put some more into it tonight, because this reception tonight is at Sebastian's expense. Thank you.
Thank you, Peter. Who would like to be first? All right. You can speak for that. Would you please say who you are and your affiliation?
Paul Sanders, ex-UCL. Well, I would like to say a few words about Pegasus and universities, because there were 5 installed. 2 minutes. Okay, you want this? There were 5 installed at Leeds, Newcastle, and Southampton. They were actually ordered on the same day. Somewhere between 9:45 and 10 o'clock, university registrars got in and got their letters from the UBC. There were these 3 orders. This is sort of mass production. There was one went to Sheffield in about 1959. One was at Northampton Polytechnic or College of Advanced Technology, Cambridge University. At that time, in the late 50s, there was a passion that the machines had to be named. This was already Pegasus, but it had to be a name as well. Leeds, they called their machine Lucifer. Leeds University Computer Installation by Ferranti, and seeing that it was actually installed in the chapel. At Newcastle, where I was at the time, we were asked about a name, and the first name was suggested was Duke, for Durham University Pegasus, University of Bolton. DUNCE, Durham University Numerical Calculating. So in the end it became 30, and there was Ferranti Digital Analyzer Newcastle. the machines were initially installed, one thing, because in Southampton, in the files, I found a rather nice receipt from Ferranti to the university, received with thanks, £35,000. Just like a growth. The machines were, of course, installed for research, but were also used for postgraduate and undergraduate courses. I'd like to mention, there was a comment about George mentioned about the program courses. And there was a belief at one time, very early in 1956, 57, that you had to learn machine code before you could be allowed to learn auto. We managed to turn this round. And we said, auto code gives you the ideas, loops and all sorts of things, and then you can go on to learn about machine code. Leeds, Newcastle and Southampton, they all used this paper-tape technical machine for doing the university administration. They all did student registration. We all shared that sort of thing. And we were able to do things which had normally taken the registrar's department about which used to take the registrar's department a whole term. And we could do this in well inside.
We need to move on.
One last thing with this. Leeds, Newcastle and Southampton, they were all, the computing labs in those places, were instrumental in establishing level brackets of the PCS. And between them, they provided 3 presidents of the PCS.
Thank you very much. Now there's a lady over there.
It's all right. I think my question's already answered. Really.
Oh, is it? All right, gentleman there.
I'm really...
Could you say who you are?
Yes, Andrew from Johnston, late 401 alias. AG. But I have memories of Christopher Strait, which I think might be relevant to the meeting. Because Hugh said, and you of course well too, that he hadn't necessarily had our people most of Mark I. All I can say is, Strachey, who I consider still to this day a genius, he programmed extensively the Manchester Mark I. In fact, he simulated, would you believe, the 401 order code so he could run 401 programs on the Mark I, because he knew he had no time to do this in what we call the exhibition. And when he came to test it on the machine, there were cigarette butts all over the floor and only 2 matches. The other one, though, I think of Strachey is that he's, I'm sure, must really be the first man who's a software guy to generate an order code. Manchester Opera was really, I think, Manchester's mixture of Ferranti and Hillman. 401 was the all engineer stuff. And he was determined to do a good job, and he did. But I'm sure he was very grateful to have George Felton, the new developer, implement it for him.
I remember him sitting at the console with the cigarette ashtray, completely overflowing cigarettes, and he would light one cigarette from the next.
Well, that.
George?
I noticed in the Pegasus there's several mentions.
Could you speak up?
I'm George Lake. Pilot Ace Deuce, laboratory. When we covered that family in one of our seminars a few years ago, there were no mentions of Pegasus, and I think that takes to something I'm not quite sure what. But looking at the comparison from Simon Lumberton's book, The Pegasus Story, page 50, as far as performance is concerned, Deuce was rather over 4 times rather over twice the speed of Pegasus, but half the speed of Mercury. In fact, we used to say to people, if you need twice the power, pay twice the price, and have that. So that's the sort of comparison. Deuce, of course, was pretty difficult to program, certainly compared to Pegasus, and it was very good at large matrix work because you put the program in, it just churned away, and you could make the programs up out of packages.
Having sold the Pegasus against Deuce, can I just say that those figures are highly contended.
Can you say who you are?
Anyone else? No one's mentioned John Bennett. Gentleman there.
Robin Shirley, I was one of the users of our Pegasus at University College, London, where I think of it as my first personal computer, because when you had time on Pegasus, you sat in front of Pegasus, and boy, it was yours. And of course, Pegasus had a couple of CRTs on the front. Mind you, they were showing binary. I don't mean some representation of binary, actual binary. But you learn to interpret it to some extent. And a little programming, we mostly used Julius programs, of course. And 2 points I want to make. One is the sheer beauty of the order code, a wonderful tribute to its designer, straight sheet. And the other point I'd like to make, since nobody seems to have done so, is the wonderful quality of the Pegasus programming manual written by George. Because as an undergraduate, I taught myself programming in Pegasus machine code, order code, by looking at that manual in the library, and I would really challenge anybody to do that on the order code for a modern computer and the manuals for a modern computer. It was so beautifully elegant and clear.
Praise indeed. Anyone else?
Peter Barnes. I installed the 9th, I think, Pegasus at de Havilland in 1957. I'd really like to sort of ask a question, because I think you were one of the very first aircraft users to actually use Pegasus Mark I for a weekly payroll for our production staff. We did 5,000 people on a weekly payroll using paper tape input, paper tape carry forward, punching at 25 characters a second, printing pay slips on 7 characters a second on color printers, and it was a fairly complicated system with overtime and piecework. And I'd be very interested in anybody else that developed Pegasus 1 in particular, with no magnetic tape and no printers and commercial.
Anyone else got some experiences to relate? I remember sitting at a dinner, sitting beside a senior manager from Old Arab. I don't think he had anything to do with the bridge. During the conversation, he told me he had designed the pre-stressed concrete roofing of the Sydney Opera House using a Pegasus. Yes. Yes.
Henry Goodland. I was going to ask George about something. George mentioned that the 23 instruction was very useful for calculating pi. Was it actually put in the order code for that of your well-known interest in pi?
Of course it was.
Gentleman back.
Harry Johnson, first driver for just a comment on the enormously scientific quality of the engineering that was going into Pegasus. At that time, Frankie was very friendly with Ericsson, Sweden, because they were our agents over there. And they were interested in getting involved in use of, I think, restricted delay. And they asked whether we would provide them with some help. So we said, yeah, sure. Send one of your chaps across to Bracknell, work with our people, and we'll tell you where we're at. And the chap came, and he seemed very happy for a while. And then he said he was going to come now. And I was sent to find out why he was unhappy. And he said, well, we realized that one of the key elements holding one of these lines is the material we use to support the line itself. And they won't tell me what it is they're using. Why? So I went about density and the youngest modulus and so on of this material that we're using. But we just do it. I don't know what youngest modulus is. And I don't know any. How did you select the material? Well, I was in Woolworths one day. And I saw some sort of gumshoe rubber stuff. And I thought, that's just what we need. So, you know, for a few pence, I bought it off to make all the design lines wherever we're doing what else. And I can't tell it. That doesn't illustrate, you know, the modern technology that was going into
The appliance of science. Well, we must draw these proceedings to a close, and I'm sure you would want me to thank all of our speakers for the wonderful, wonderful contributions they've made. It's been very nostalgic for all of us, I suspect, but particularly for me. And I thank you for the privilege of being your chairman for the afternoon. Not all of you are able to go to the receptions later this evening. There isn't enough room around the machine, unfortunately, for everybody to be present. So the numbers who will be attending the reception have been limited to those that had a more direct involvement in the design and use of the machine. I'm very sorry that's the case. So some of you, I'm afraid, must leave, and leave now, if you're going to get out of the building. Thank you very much.